Hello, everybody. Welcome back. Today, we're going to be talking about the general exponential function derivative. Okay, so the general exponential function derivative has to do with the natural logarithm and ln as well. So, given any general exponential function, y equals b to the power of x, then y prime is equal to b to the power of x times ln b, so the natural logarithm of b, okay? Now this is different from e to the x, right? Because again, e is a fixed value, right? E is a specific exponential function, right? And if we think about it, well, let's say we apply this rule to e to the power of x, we get e to the power of x times ln e, which is just 1, right? Ln e is just 1, they cancel, so we get e to the power of x. So we can still apply this rule to the natural logarithm, it's just that we'll end up getting the same thing. Whereas for general exponential functions, we're going to be needing to use ln, right? We're going to need to multiply by ln of the base, right? So b denotes base here in this situation. Okay. Now, what about the chain rule for an exponential function? It's going to be to do ln b and also to do the derivative, right? Take the derivative of what's in our exponent. So we're kind of combining this rule over here with the chain rule. We're putting them all into one. So I'm going to give you a few examples. The first example is find the derivative for 4 to the power of x. So to do that, I'm just going to repeat 4 to the power of x because that's the first thing we do here, and then times ln 4. And there you go, there's our answer. It's 4 to the power of x times ln 4. All right, how about the second example? It says find the derivative for 8 to the power of 3x plus 2. So for this one, we're going to need to use the chain rule. So the chain rule, again, it states that that if y is equal to b to the f of x, that y prime is b to the f of x times ln b times f prime of x. So let's do that, okay? So in this case, the derivative would be, well, the first thing is just repeat the original. So I'm going to just write down what we have originally, times ln b, so ln of the base. So in this case, that would be ln 8. And then times the derivative of what's at the top. So what's the derivative of 3x plus 2? Well, it's going to be 3. So therefore, if I just rearrange this in a nicer order, I would have this. But even that first step, that does give us the answer. It's just ordered a little bit strangely, I would say. But yeah, there we go. That's how you do it. Okay, this next one is very, very similar, example 3. So I advise you to pause the video, try this on your own, but I will take it up after. Okay. All right, awesome. So let's do this one next. F prime of x is equal to, well, f of x. So same thing as before, I'm just going to copy it, times ln of b, right, ln of our base, so ln 7, times the derivative of what's on the top. So what's on the derivative, I should say, of the exponent. So derivative of 2x plus 4, x squared plus 4x minus 3 would be 2x plus 4. Voila, there we go. We did it. All right. Yeah, there we go. I'm just going to leave it like that. Actually, I don't know that there's necessarily a better order that I can really think of, so we'll just leave it like that. The main thing is when we have like a coefficient, coefficients generally go at the front. We don't really have a coefficient here, so as far as I know, there's not really any order that we should be putting these in to make it look nicer or anything. So yeah, you can rearrange the order or not. I don't think it really makes a difference. Okay, let's try this next example. It says to find the derivative for 3 to the power of x over x cubed. Okay, so here we're going to have to apply the rules we learned today about how to find the derivative of the exponential functions, and also we'll have to apply the quotient rule. So just a reminder, the quotient rule states that if y is equal to f of x over g of x, then y prime is f prime g minus f g prime over g squared. Okay, so g of x cannot equal to 0, which is good because g of x cannot be equal to 0 by the quotient rule, but it's not, so we're good. Okay. All right, so let's apply this. And again, there are full videos on the quotient rule specifically. If this is unfamiliar, do make sure to go watch those and figure that out if that's the case, because that is all I will say on it here. Okay, so what's the derivative? Well, the derivative is going to be the derivative of the top, right? So derivative of 3x, or of 3 to the power of x, which is going to be 3 to the power of x times ln 3, and then that's times our bottom, which is x cubed, minus the top, which is 3 to the power of x, times the derivative of the bottom, which is 3x squared, and that's all over x to the 6, right? Because x cubed squared is going to be x to the power of 6. So there's actually a few things we can kind of factor here to make this a little bit more digestible for us. So I'm going to do that. I'm going to say this is 3 to the power of x squared times x ln 3 minus 3 over x to the power of 6. And from there, we could actually, I guess we could knock off a couple of those, and we could say this is 3 to the power of x over x to 4, x ln 3 minus 3. And you know what? I think that's as simple as we're going to get it. I think that's as good as we're going to get it. I don't foresee any other things we can do to make this a little bit more simpler for us. But yeah, there we go. There we go. We applied the quotient rule and also the new rules we learned about how to differentiate an exponential function. Okay, let's try this one here. Here we have the natural logarithm again. So that's good. We remember that from the last day, and or even if we did apply this rule, we would still end up with the same result, which is good. And also here we're going to apply the product rule. Oh, and also we're going to apply the new rule we learned because we have an exponential other than our natural exponential with e. So if we apply the product rule here, we're going to get e to the 4x times 4, right? Derivative of the first times the second. So I'll just copy the second. And then plus the first one times derivative of the second, which is just going to be the original times ln 2, right? Ln of the base times 5. And then I'm going to make this a little bit neater. Let's put the 4 here. And then let's put the 5 out in front. And there we have it. I think that's as good as we're going to get it. That's at least that's as much as I'm going to do. We could factor it here, but factoring wouldn't allow us to cancel or anything like that. So I'm just going to leave as is. Okay. Now let's do our very last problem today, and this is a challenge problem. It says, on January 1st, 1850, the population of Goldrushton was 50,000 people. The size of the population since then can be modeled by using the function p of t is equal to 50,000 times 0.95 to the power of t, where t is the number of years since January 1st, 1850. Well, that's interesting. I feel like normally the populations increase over time, but this population is actually decreasing by 5% a year, right? Because we have 0.95 over here. So after 1 year, it would only be 95% of what it was the previous. And then it's only going to be 95% of what it was the first year during the second year, and so on. So we're losing 5% per year based on whatever the answer of the population was last year. Good work. Good work. Very well done. Okay. So the first question was, what was the population of Goldrishton on January 1st, 1900? Well, this is 1850. So January 1st, 1900 is exactly 50 years after January 1st, 1900, right? So for A, all we need to do is find P of 50, right? Because it's 50 years after would be the time, and that is going to be 50,000 times 0.95 to the power of 50. Oh, oops. And that's going to be equal to 3847.25, which we could just perhaps round down a little bit to 3,847, because I don't really think it's possible that a quarter of a person is part of the population and the other three quarters of them is not part of the population. So I'm just going to assume that we're just going to round that down and say about 3,847 people is the population. So therefore, the population is about 3,847 in, or I should say on January 1st, 1990. And that might seem like, oh, that's way less. Didn't we just 50 years ago have 500,000 people? Or sorry, 50,000 people, not 500,000 people. And yes, that is true, we did, but this is 50 years later, 50 times that we're taking away 5%, that adds up, right? It really doesn't surprise me at all. I'm not sure why people are leaving this town at such a high rate, but maybe they don't like it as much, or there's more job opportunities elsewhere, who knows. But this is the correct answer regardless of what our instinct might be about it. Okay, then B asks, at what rate was the population changing? Was it increasing or decreasing? So actually, first part of that question we can already answer, it's decreasing. Now, we will figure that out algebraically when we figure out that the derivative is going to be negative at this point. However, we can already tell that the population is decreasing even just by looking at this function, right? That the over time that the function decreases because we have this number is less than 1, right? If this number is greater than 1, this base is greater than 1, then the population's increasing. But because it's less than 1, we're decreasing. We're decreasing and losing 5% of our population every year. Okay, so to find that rate, what do we need to do? We need to find the derivative. Awesome. So there's our derivative. It's 50,000 times 0.95 to the power of t times ln 0.95. There we go. So that is going to be, if we plug in 50, it's going to be 50,000 times 0.95 to the power 50 times ln 0.95. Now we've actually already found this value, right? We already found that up here, that it was 3,847.25. So we have a little shortcut where we can figure that number out. I'm going to plug in the exact value that I got, even though it doesn't quite make sense for that to actually be the population exactly then. I'm going to plug in the exact answer we got in order to find the rate of change more accurately, as opposed to my rounded version, given my assumption that we couldn't really have just a quarter of a person. Okay, times ln 0.95. And that is equal to negative 197.34. So therefore, it is decreasing at a rate. The town is decreasing by 197.34 people per year after 50 years. Past January 1st, 1850. Or I could have just said on January 1st, 1900, but I didn't think of it. But yeah, there we go. There's our solution. All right, well, that is already it for today. Very good work today, and I will see everybody next time to talk about. Oh, we already did this one. It'll be to talk about optimization problems involving exponential functions. So, kind of combining what we learned in Unit 3 with what we're learning now. So, very similar to Unit 3 and very similar to what we've just done. But yeah, that's it for today. Bye, everyone.